So let me just recall where we were. So we have our map 5G, right? So given a directed graph, we have a map that takes the edge coefficients lambda and the variances omega and sends it to the covariance matrix, right? So this is a covariance matrix for a Gaussian distribution, and the image is this NG, which is a subset of the positive definite n by n matrices. And well, the question we were discussing last time was that given a sigma in this model, we can think of it as a perfect estimate. Can we actually recover the lambda and the omega? So this is an important question in statistics. Can we actually estimate the parameters that define our model? And so in mathematical terms, it just means, is this function injected, this parameterization? And so I gave a general definition with thetas. So I'm going to use that notation. So theta, I'm just going to call the parameters, lambda and omega. And the big theta is the full parameter space. In this case, RD reg. Remember, this was all matrices that have zeros in the right places. Namely, there's a zero whenever there is no edge between I and J. And these are diagonal matrices that coming from the omega. And so we call the graph G globally identifiable if this is injected. That's the best case. However, sometimes we need to relax to generically identifiable. So this would mean that we only have that the fibers are singletons for almost all theta and theta. And we talked about how this in algebraic geometry, that's what we call name generic, right? So it would be for generic theta. And algebraically identifiable is when maybe the fibers are not singletons, but they are at least finite. Again, for generic theta. And so if we're not in any of these cases, then it will be not identifiable at all. So we just call it not identifiable, and that's a bad model. Okay, so we looked at a couple of examples. So the first example was this, just the simple graph that goes from 1 to 2 with an edge weight lambda 1, 2. And so I wrote here the map 5G explicitly. This you should remember from last time. And given a sigma in the model, the question is, can we recover omega and lambda? And we actually did this last time. And so if you remember, omega 1 is simply sigma 1, 1. So you need to solve this system of equations, right? This equal to this equal to this, and this equal to this. Okay, and in this case, it's easy enough that we can just solve it by hand. And so omega 1 is sigma 1, 1. Lambda 1, 2 has to be sigma 1, 2 over sigma 1, 1. And finally, omega 2, right here, omega 2 was sigma 2, 2 minus sigma 1, 2 squared over sigma 1, 1. Oh no, it's times sigma 1, 1, I think, right? So we'll check. Lambda 1, 2 squared. No, yeah, there's a sigma 1, 1 squared, and there's only one sigma 1. So I think that's correct. Okay, so this means this is an instance where this graph is globally identifiable. Okay. We saw another example, which was the 2 cycle. So lambda 1, 2 and lambda 2, 1. And I argue that in this case, it cannot be identifiable. So not identifiable. And the reason was that we have a 4-dimensional parameter space, right? So we have a 5G that sends lambda 1, 2, lambda 2, 1, omega 1, omega 2. to PD2, which are matrices of the form sigma 1, sigma 1, 2, sigma 1, 2, sigma 2, 2. Right, so it's almost be symmetric. And so we have 4-dimensional space mapping into 3-dimensional space. And so that's why it cannot be injected. And just for you to try, I'm going to give already an exercise that we're going to discuss tomorrow during the tutorial. So I'm going to already announce it, and maybe you can even already try it. And then that will be more rewarding when I give the solution tomorrow. So I'm going to write exercise. Let's say I'm going to choose some particular values of lambda and omega. So let's say I'm going to choose lambda 1, 2 equals 1, lambda 2, 1 equals 2, omega 1 equals 3, and omega 2 equals 5. Okay, so I'm going to choose this, and the first part of the exercise is to just check, verify that if you apply 5G to these parameters, you're going to get a covariance matrix, right? You get a covariance matrix that's in the model. And if I do my computations correctly, they should be 23, 13, 13, 8. So that's the first part. Check that this is true. And the second one would be to find, so if this is not identifiable, I claim that the fiber of this point is infinite, actually. So I'm going to say find infinitely many omega lambdas, infinitely many pairs, such that 5G equals the same. Right? So saying the fiber of this point is actually infinite. And I mean, I just took a particular point, but this happens for generically. Because it happens for any point that you choose, you're gonna have this infinite fiber. You can also try your own. But yeah, so okay, this is just an exercise to find such fiber in this case. And there was one more. Maybe I'll. Okay, I can still squeeze it here so that I don't lose what we have. So I think I had the 3 cycle. So lambda 1, 2, lambda 2, 3, lambda 3, 1. And we said, well, this one actually has a chance because now it's 6 parameters versus 6-dimensional space. And indeed, it turns out, well, unfortunately, it's not globally identifiable, but it is algebraically identifiable. It's also not generically identifiable, but it's algebraically. And I'm also going to give you an exercise in this setup. So let's see. But one of the good things of having is this that iPad is that I can rearrange things a bit to make space. Okay, so this was the first exercise. So here I'm also going to give you some exercise. So in this case, I'm going to choose a particular omega and lambda again. So I'm going to choose in this case omega 1 equals 1, omega 2 equals 2, omega 3 equals 4. And then lambda 1, 2 equals 1/2, lambda 2, 3 equals 2, and lambda 3, 1 equals 1/2. Okay. And so if I do this, the first part is again verify what sigma is. And sigma in this case, again, if I didn't make a mistake, the sigma now should be 3 by 3. It should be 16, 12, 28, 12, 10, 22, and 28, 22, 52. So that would be my sigma. And then the question is now find another point in the fiber in this case. Okay, so the second part is kind of the same, just compute the fiber, but now it's not infinitely many. So find another omega lambda that has the property that phi g of omega lambda equals this. And I already gonna tell you there is exactly one other point. Here I can see. Oh, I can see myself. Okay, so there is exactly one other point. So I'm gonna tell you already that the fibers here, this finite number, is generically it's 2. So you can see that this map, phi, is generically 2 to 1. So that is interesting, right? So and well, as an exercise, I propose to you, at least for this particular case, to find the other point. Like, how does it look like? Okay. So I hope the exercises are clear, and tomorrow I'm gonna give the solutions in the tutorial. Okay, so you can see then we have the three behaviors here: globally, not identifiable, algebraic identifiable. A natural question is, how can we decide in what case we're in? And well, thankfully we have a theorem. And this is going to be the theorem. And this is one of the, let's say, main results that we have been leading towards. So I'm going to use actually to discuss the proof things from even the first lecture. So the theorem is easy. The theorem just says that if G is a DAG, then G is globally identifiable. So one more reason for which we always like DAGs, because then we're in the best case where we have global identifiability, and so this was just one instance where we had this DAG that's globally identifiable. These were not DAGs, right? And so I want to give you at least a proof sketch on just like what's the main ingredient of the proof. And the main ingredient is to show, what do we want to show, right? So we want to show that the phi g is injective, right? It's injective on the parameter space, which is Rd cross Pm diagonal. And here I'm already using one of the facts that Rd reg equals Rd if G is a DAG. You remember this? We discussed it a couple of times. That the regular parameter space of this Rd is actually Rd equal to Rd reg. So Rd reg equals to Rd, the full Rd, if you have a DAG. And so, okay. And so I'm just gonna tell you what the inverse is. So we'll give explicit rational inverse. And so how do we find this? Okay, so we can assume, as is the case with DAGs, is that we have a topological ordering. And then we inductively look at each vertex. So in this case, j in M. So I'm going to start from j equals 1. For j equals 1, and actually any j such that it has no parents, so the set of parents is empty, we have. So here I'm gonna again say I'm gonna use things from all of the lectures at this point. And so the first thing I want to use is that the sigma jj, right? So the entry jj in the parameterization, right? So in this map, if you look at the diagonal jj, what is this? Well, in the case where this is empty, then we had, in general, we had the track rule. We had this track rule, which is here. So I already copied it for you to remember. So track rule that told us precisely how to express the entries of sigma in terms of tracks. So remember, this was tau was a track that goes from I to j. This was the top of the track, and these were the two directed paths from the track, right? So if you remember, if you have a track, you have the top, and then you have two directed paths that come down here to I and here to j. But if we are in the case where I equals j, and this particular j has no parents, then the only possible track is the empty track, where you only have, there are no edges, and you only stay at t, right? So that's the j is just the only track, which means that we would only, these monomials are going to be 1 because they're empty products, and then this w top is just the wj. So my claim is that sigma jj is simply wj. And so this is one of the ways to have the inverse for sigma for wj, right? So if j is 1, or in particular any one that has satisfied this, the wj associated to that particular j is just simply sigma jj. And observe that this is the case in our, if I go back here, right? So this was the case. The W1, the omega 1 was simply sigma 1, 1. So this is just the generalization, right? It happens not only for 1, but for any such j that has no parents. And so, okay, so this is one way. And now I can move down, right? And eventually I'm going to have things that have actually parents. And then I have to look at what I'll get. So, okay, so now I'm gonna write. Now we look at j with actually parents. And so we can write, if you remember, again, now this is going back to the first lecture, xj is the sum, I guess actually this was the second lecture, when I defined the linear central equation model, lambda ij xi plus epsilon j, right? This is our system, how we define the model. Okay, so this we can rewrite as lambda j. Was there a question? Okay. J parents of j. Let me finish writing it and then I explain what this means. Okay, so this is just a way to rewrite this. Remember how we wrote it? We had this x equals lambda transpose x plus epsilon, right? That was the matrix vector notation. But now I'm only looking at the entry xj, which means that instead of having the full lambda transpose, I only need to look at a particular row. And this is the row corresponding to J. And here I only care actually about the parents of J, because anything that's not a parent automatically is 0. So this is the submatrix that's 1 times cardinality of parents of J that from lambda. And then I will multiply by the vector that's equal to size x parents of J plus epsilon J. So it's just rewriting this, but now in a vector times vector plus some epsilon J. And so why do I want to write it like this? Because this is going to be helpful to write down the actual inverse by looking at this. And so why? Well, we know, now this is really from the first lecture, and this is this blue thing that I have down here. So recall that the conditional, well, we proved 2 things about Gaussians. Well, at least we mentioned two important properties of Gaussians. And these were that if you have a Gaussian, you have a disjoint A and B, then the marginal is always a Gaussian, where you just take the subvector with entries in B and the submatrix with rows and columns in B. And relevant for us now, the conditional density is also Gaussian, and this is the mean and this is the covariance matrix for that Gaussian. Okay, so I'm gonna do that now. I'm gonna take A to be just the singleton J, and B is gonna be the parents of J. So maybe I'm gonna write that. So by taking A equals just J and B equals parents of J, so let's see if I write this correctly so you can help me check. Xj given x parents of J equals little x parents of J will be Gaussian. What dimension? Well, cardinality of A. Cardinality of A is 1. So this is a univariate Gaussian. This is just a single. So I don't write 1. I could write 1. Usually you don't write it. And so, okay, and what is the mean? Well, the mean for us was 0, right? If you remember, so we took all the variables to be centered. So mu A and mu B are 0 automatically. So I just care about this part, sigma AB, sigma BB inverse. So this would be sigma J parents of J times sigma parents of J inverse times x parents of J. That's going to be the mean. And the variance is sigma AA, and sigma AA is just sigma JJ, right? Because that's the entry, actually, JJ, minus sigma J parents of J, sigma parents of J inverse times sigma parents of J. Okay. And so this is just using this result, and that's why I wanted to recall it. But now that we used it, I'm gonna remove it. So this was already instantly we saw before. Okay, and so now that we have it like this is nice because now I can take variance and expectation. So for example, taking the variance, I have now 2 expressions, if you see. So I have this conditional expression for any value of the parents of J, which is going to give me this variance. So I'm just going to write it, maybe. Okay, actually, I'm going to be a bit lazy. I'm just going to copy it. So we have this. And this on the other side, we have this equation. So xj, given the values of all the parents, that means that now we have an expression that xj is something, a constant, plus epsilon j, or if you want to see it here. If you already fix x parents of j to be a little x parent of j, this is just a constant. So when you take the variance of xj given this is just the variance of epsilon j. So so how do I write this? Let's see. Taking variance in both sides, right? So I want to take the variance here and take the variance here. And if I do that, then I get the variance of epsilon j. But the variance of epsilon j is omega j. Right? That's how we defined it. That was the definition of omega j, the variance of the error. And so now we got an equation for omega j completely in terms of the sigmas. You know, it's a bit complicated, but now this is everything in terms of the sigmas. So you should be able then to compute any omega j that you want, not just for the ones that have no parents. And we can actually check, I think maybe it's worth it to check that this formula is true here, right? So remember, this was what we computed. Omega 2 is this. So I'm gonna copy it, put it here. Maybe I'm gonna put it in green. Okay, let's put it in blue. So let's see, I'm gonna tell you this formula is true. If you now substitute j equals 2, what do you get? Maybe put this here. I substitute j equals 2. What do I get? Sigma 2 minus sigma. So what is this? This is j equals 1, and the parents of j, j equals 2, and the parents of j is 1, right? Okay, so here is the graph. Okay, so j equals 2, the parents is just 1. So this means this is just the entry sigma to 1, which is sigma 1, 2 because it's symmetric. And then parents of j, that means sigma 1, 1 inverse. And then here we get sigma 1, 2. And look, that's exactly the same. Sigma, as I said, sigma 2, 1 equals sigma 1, 2. So we get sigma 1, 2 squared divided by sigma 1, 1. So at least it works in this case. But now I gave you the general formula for omega j. And to obtain the lambdas, we need to just now take expectation to find the lambdas. And so again, the mean is this according to the conditional distribution. But on the other side, if I take expectation on this is a constant. So the expectation is going to recover this lambda j parents of j times this, and the expectation of epsilon j was 0, if you remember. So these were the errors. And so what do I get? Well, I get that this is equal to lambda. What is expectation? Yes, lambda j parents of j times x parents of j. And this holds for all the values of x parents of j in R cardinality parents of j. Right? So this holds for all possible values that you can condition on. So this means that you can cancel it, right? And so then you get. So I'm just going to give you now the formulas in a nice way. Like I'm gonna try to have it in a nice way. So j parents of j, sigma parents of j inverse sigma parents of j, and omega j parents of j equals sigma j parents of j times parents of j inverse. Okay, so this is the explicit inverse that I promised. Okay, so this gives me all the solutions for omega, and this gives me all the lambdas that are coming for so for j and its parents. Okay, so and then since we are going down, you keep going down, and then you're going to obtain all the lambdas for those parents of j. And then you go through the graph, it's a DAG, so you know you're going to end and everything is going to be consistent. And then these are the answers. So you can also check, for example, maybe we can do it here also, right? In this example here, what would be the lambda 1, 2, according to this formula here? Lambda 1, 2, which I guess I should actually write lambda 2, 1. Oh no, lambda 1, 2, it should be lambda 1, 2, sorry. So j equals 1, no, j equals 2. Okay, so it's j equals 2, okay. J parts of j. So lambda 1, 2 has to be sigma 2 and 1. So this will be sigma 2, 1 divided by parents of j, which is sigma 1, 1. Okay, I mean, everything is 1 times 1, so that's why it's increasing. As you can see that this is exactly the expression we had before. Where was it? Here. So it matches. Again, this big formula matches the specific case. All right. So this is it. Okay, I think I maybe took already longer than I expected, but I wanted to make it at least have like a proof that incorporates, you know, all the elements I said from the first 3 lectures. Okay. So unless there are any questions about this, I would move on. And well, I want to talk about a corollary, important corollary. And it's the following, is that if you have a DAG, the dimension of the model, but it's a very important invariant, right? The dimension of the model can be computed simply by counting the number of vertices and the number of edges, and then that's going to be the dimension. So it's going to be the expected dimension. Okay, so this 5G map is mapping my space of parameters into a full dimensional space, which is, I mean, full dimensional in the sense as the number is preserved, right? So this is going to be in MG, of course, is a subset of PDM, right? Which is cardinality of B, with what we usually call M. And so the dimension is always bounded. If cardinality of B is M, know that the maximal dimension is attained when you have the maximum number of edges that you can have. And that will be for a complete graph. With a complete graph. And how many edges are there for a complete graph? If these are that you tell me. Anyone here or there? So if I have a graph with m vertices, how many edges are there if I have a complete graph?
choose two.
N choose 2, exactly. So N choose 2. So that will be, there is an edge always between any two, right? Remember, it's just directed. And so, okay, we have a complete graph. And so that means that the dimension in that case is gonna be M plus N choose 2, which is N plus 1 choose 2, which is exactly the dimension of the full space, PDM. Right? So that's so when you have a complete diag, you actually reach the full dimension PDM. And so okay, but that's usually not what you want. So usually you want graphs that are sparse so that you can actually see what's going on and you have some structure. But okay, so this is just a nice corollary because this is, as you know, if you study algebraic varieties, for example, and fundamental invariant is the dimension. And then the degree, for example, would be another fundamental invariant. Okay, so this is great, but there is an issue. So great, but we only considered exact estimates, right? So we considered a sigma that's in NG. Right? So but in practice, we only have a noisy estimate. So we only have a noisy estimate sigma hat. That's not perfect, right? So of sigma. And so what can we do? So for example, a typical estimate is given by the sample covariance matrix. So maybe I'm gonna remember that. That's the point. So for example, S equals 1 over n. Okay. Let me go back a bit. So from a sample, x1, x2, xn. So now I finally get to use n. Right? So I've been avoiding n, so maybe n would have been natural for number of vertices, but n I wanted to reserve because in statistics n is the sample size. So from a sample x1, x2, xn. So what is this? So these are vectors in Rm. Each one of them is a vector in Rm. And the idea is that I observe our variables. So we have x1, x2 up to xn. This is a vector of observations, right? So remember we have our in this case, let's say this is here. I would observe the values for x1, the values for x2, the values for x3 once, and I would put that into this vector x1. And then I observe it again, and I put it into x2. And I do this n times, that's my number of samples. And so from here, I want to have some estimate of sigma. I want to say, okay, what is the covariance for this model, for this configuration of random variables? And so the sample covariance matrix is very useful for that. So the sample covariance matrix is defined in this case as the sum I from 1 to n of xi transpose. So I'm gonna create this, and I'm gonna call this, here's an important name, sample covariance. Sample covariance matrix. And so yeah, observe this is indeed a matrix. So this is gonna be an m by m matrix, which is the correct dimension. And why is this useful? Well, it's an estimate that's nice because the expectation of S will be the expectation is linear, right? So this will be sum 1 to n of the expectation of xi transpose. And well, here it's a key question. This expectation of xi transpose. So here I need to remember, maybe you remember this from the preliminaries in the first lecture. So the variance of a vector this is the covariance matrix of a vector, can be written as the expectation of x times x transpose minus expectation of x times expectation of x transpose. Okay, so this is one of the formulas, important formulas for the variance in terms of second moment and first moment squared. So yeah, in one dimension, this just says it's the typical formula. Variance of x can be written as the expectation of x squared minus expectation of x squared. So it will be m equals 1. And so, okay, I'm using this because since for us the expectation is 0, I can forget about this, and this expectation of xi transpose is the variance. And so the variance is sigma. So what do I get here is just that n copies of sigma. And now I have to be careful that the sum doesn't get confused with the sigma. But you can see this is n copies of sigma that is average, so we get sigma. So what I'm trying to say here is that this is in principle a good estimator, because as n goes to infinity, well, we know so that this s should converge if you average, or like, sorry, okay, let me say this like this. So this s, as in on average, the values for this s are going to be around sigma. Right, so that's one of the properties. So we call this unbiased estimator, right? In statistics. So this is an unbiased estimator of sigma. Okay, so I hope that was not confusing. And so, but the question remains, so we only have this s, and then how can we estimate our parameters in this case? Like, for example, if our g were just like we had this example, remember? This. For this model, we computed that the IG, the ideal associated to this model, was sigma 1, 2. In other words, 1 and 2 are always independent. So x1 is independent of x2. Another way of saying it, in the MG, the sigma 1 to entry was always 0. So this dimension of the model, which now we know because it's the number of vertices plus the number of edges, is 5, which is less than 6, which is the ambient dimension of 3 by 3 symmetric matrices. And so, I mean, this is the equation. It's a hypersurface, right? It's actually a linear space. And this is given by sigma 1 2 equals 0. And so, yeah, if I just take an S, right, a random S that I created from data, S11, S12, S13, S33, S33, this S will not satisfy that, in particular, this is 0. And any lambda omega that you take, right? So how do I say, like, there is no lambda 1, 3, lambda 2, 3, omega 1, omega 2, omega 3, such that the phi hits this S, right? So even though this S may be close to sigma, since it's close but it's not exact, I will, with probability 1, I'm going to miss it, right? Because I'm in this lower dimensional set, and this S is going to live in the full dimensional, it's just a positive definite matrix. And so this is an issue, right? So I cannot actually solve, I cannot even think about this identifiability, because in practice I have this. How do I find lambda and omega if I cannot solve this? There will be no solution for this system, if you think about it. And so okay, so that's when maximum likelihood estimation comes in. And so that's what I want to tell you about in the last part. And so this will fulfill my promise in the abstract I gave and in the title of my lecture, where there was likelihood geometry. So I promise at the end I'm gonna have defined all the things, all the words in the title. So the last one was likelihood. So maximum likelihood estimation, and this also makes Aida happy because she was relying on me to define ML estimation. So okay, so I'm just gonna give the big idea. And so the general idea is you remember the density for the Gaussian. Hopefully. Very good. I heard a yes. So this was 1 over the square root of determinant 2 pi sigma e to the minus 1/2 x. So our Gaussians are centered. So I'm just gonna write x transpose sigma inverse x. So this is the multivariate Gaussian, mu is 0. And so we have the data from the previous slide, x1, x2, xn. So the idea of maximum likelihood estimation is to maximize the likelihood L let me hold capital L sigma, maybe like this, Lx sigma, which is given by multiplying f evaluated at xi, like this, I from 1 to n. So the idea is for each sample that we obtain, we evaluate how likely it is by just substituting into this function, right? So this function is a bell-shaped density, right? So in 2 dimensions, it will look something like this. Like if you think about it as a shape, it's like a bell-shaped curve. That's bell-shaped surface that's going down on both sides, and it's decreasing exponentially. And so for each x, we plug in and we have a value, and this will depend on sigma. And so this product, we want to find the sigma that's going to make this as likely as possible, the data as likely as possible. And so the so-called maximum likelihood estimator, MLE, is the maximizer of this. So it's sigma hat equals R max over sigmas in your model, M. In our case, it's going to be mg. But if this works for any m, so I could actually just call it m, of Lx sigma. And so m is a model. So m is a subset of PDM. Model. Okay. So for us, this would be mg. But this is in general. So this is the idea in maximum likelihood estimation. And well, let's maybe write this a bit more carefully. So most of the time, this is a bit nasty because it's a product of this and this. But if we take the logarithm, it's nicer. So if we just take the logarithm, Lx sigma equals logarithm of capital L x sigma. So what do I get? So now I'm gonna substitute these in here. So I'm gonna get the sum I from 1 to n. Okay, and let me get rid of these constants quickly by writing minus 1/2 log that 2 pi sigma. And then here I will just get the sum 1/2 sum 1 to n xi sigma inverse xi, xi transpose. I'm sorry, xi transpose sigma inverse xi. Okay, that's what it is. And so let's rewrite this in a nicer way. So the logarithm of the determinant, I'm gonna take the 2 pi out. The 2 pi comes out from the determinant raised to the m, right? Because this is an m by m matrix. So this is actually, and this is the same term n times. So I'm just gonna get minus mn over 2 log of 2 pi. And now I get the log that sigma. Okay, and then minus 1/2. And here, one uses the so-called trace trick. Because this is a scalar, so I can just write it as trace of that. But that's useful for us because then in the trace, we can rearrange, right, by properties of the trace, we can then rearrange this as xi transpose. It's very sneaky. And so if we do that, so I'm gonna now drop this constant because this will not affect how you maximize. And so let me write like this, minus n over 2 log that sigma plus I factored the 2 already, and there is an n here that I'm gonna put inside the trace here. And so I'm gonna get the trace of sigma inverse s. And so, sorry if I was maybe a bit quick here. I mean, you can check the details, and you can ask me if there are any questions on that. But basically, what I want to tell you is that this likelihood function, log likelihood function, then the problem of maximizable estimation will be equivalent to maximizing. So ML problem is equivalent to minimizing the function log that. So okay, let me write it like this. I mean, it's true what I said, but then let me just write it like this. Sigma hat argmin over sigmas in ng of this function. Log that sigma plus the trace of sigma inverse s. Okay, so this is a nice, maybe this is a bit hard to remember for the full likelihood, but this is a nice expression that one can remember. And so the idea is like to find the optimum sigma hat, this will be automatically in ng, right? So what we had before is we had our variety, and then we had a point outside the variety, S, and now we're projecting it in a way into mg. Right, so this was the variety mg, and our model, and now this have this sigma hat here. So we're trying to find the best point in the model that's going to explain the data, and this is given by this minimizing this, and so the so-called ML degree, which I referred to, so the ML degree of the model of M, or in this case NG, I said, but this is in general, I said for any model, is the number of critical points of this function. Okay, so here of this on MG closure. And so this M, oh sorry, I wrote G because I'm already thinking about G. Okay. And here, this closure, this is a Zariski closure. So this means they can be complex. So this is important. This could be complex. And this for generic S. Okay, so maybe this is a lot to take in, but the idea is so you have a random S, that's the data, and then you have this function, you take the gradient of this function, and this looks maybe not so nice algebraically, but it's very nice when you take the gradient, because the logarithm of the determinant, when you take the derivative of this, you're gonna get 1 over the determinant, and then the determinant is polynomial, right? So then you actually get something polynomial. You get a rational function, and so this is a system of polynomial equations, rational equations, and the number of critical points is gonna be constant. Generically, and that's this is the famous ML degree, which is an important invariant in algebraic statistics. And so this is the definition in general. Let me conclude with an example. I already have this here. I don't think maybe I won't do, but okay. Which is just an example slash theorem. What does this mean in our context? Well, I'm already gonna tell you the nice thing, and the nice thing is that if G is a DAG, then MG has ML degree 1. And ML degree 1 is the best thing you can hope for, because that means there is a unique critical point. And that unique critical point has to be the maximum likelihood estimator. It's the one that maximizes or minimizes this in this case. And so that's great. And I'll tell you what it is, just in words. The MLE is given by sigma hat equals 5G of lambda hat omega hat, where lambda hat and omega hat are the classical least squares estimator. So if you have taken any statistics course or introductory course in econometrics, for example, you've seen linear regression, and this shouldn't be a surprise when you think about linear regression. So where is our model? Somewhere here I wrote it. Here, right? If you're trying to estimate the lambdas, if you have data x here, xj's and xi's here, this is a linear regression problem. You're trying to find the best coefficients that are going to fit, right? You think about fitting a line, or in this case, fitting a plane, to make it go through these points. You're not going to find something perfect, but you're going to find the best estimators, the least squares estimators. And it turns out the least squares estimators are precisely the ones that are going to give you the maximum likelihood estimators, and are going to give you your sigma hat. And so this is they already. Yeah. So this is the nice news. And well, you can have examples, and in this example that I had given you with 1, 2 pointing to 3, it turns out the given S. Again, so S11, S12, S13, S22, S23, and S33. It has to be symmetric. The MLE is sigma hat, and then I put this here. So I didn't want to copy it, so I have it stolen from my paper. Yes, so the S's should be actually the S's are correct. So you can see here there will be zeros because it must be in the model. Remember that this model is defined by sigma 1, 2 equals 0. So my estimate should have a 0, otherwise it's not even in the model. And so this has a 0, and then there are other things that you can see here. But everything is in terms of the S's, and what you can see is that everything is a rational function in terms of the S's, which is consistent with this ML degree 1. So everything is as nice as you want algebraically. Okay, so this was the example I wanted to say. You can read more about this example and general MLEs for DAX, and so this should be a paper. I can put the reference. So it's a paper joined with Lucas Gustafsson, Orlando Marigliano, Kathleen Kohn, and Anna Siegel, and we try to understand the algebraic generic structure for such ML degree 1 estimates for Gaussian bonds. Okay, so I think I will stop there, and thank you everyone for your attention.
Okay, Danish, you are the moderator.
Okay, so question from here. I have just questioned in the last.
Yes.
You have the remark that this is consistent with the ML degree 1. I do not understand how we get this.
Yes, okay, this is a good question. So the idea is that when you're trying to solve this system, this is going to be in the end an algebraic system, and you can use, for example, Grosvenor basis to try to solve it. And a Grosvenor basis would typically, if you think about an elimination ordering, like graphic ordering, you're going to have one variable that's a single equation in one variable that you can solve and then backtrack, right? And so the degree of this last equation is going to give you the possibly multiple solutions, which is going to be this is the ML degree. You're going to see it as the ML degree. And so if you have an ML degree 1, you know there is a unique solution. So that means that the equation you get at the end has to be a rational function. So that all the parameters are going to be just rational in terms of the data, in this case, the S. And so that's what I meant here when I said ML degree 1. I expect then my solution, my critical point, to be rational function in terms of the S's. If the ML degree were 2, then I would expect to have some square roots around, because then it's a quadratic equation. Yeah, thank you for the question.
Yeah, I have a question. If you have a dense matrix, covariance matrix, how do you specify it?
Well, that is a great question. That I haven't talked about. But that goes more on the direction of how to choose your model, right? So far here I have assumed that we know G, right? G is given, and then we have the data, and we're trying to fit it to G. But in practice, you don't even know G, and you're trying to find a sparse G, but that a sparse G that will actually try to fit your data. So you have this kind of model selection idea when you want something sparse, but you want something that will fit good, but you don't want to overfit. So the best way to fit the data would be just to take the complete DAG, because then we saw that then it's just, you don't even, the MLE would be just the same matrix. There would be nothing, but then that you don't understand anything. I mean, there are no relations, right? The ideal is just the zero ideal, right? Yeah, so that's a good question. I think maybe I'll touch on it tomorrow if there's time.
Any other question? Yeah. Dr. Imran, from your side.
I don't. No question from our side at the moment. Okay.
Thanks to Dr. Carlos.
Thank you.
We have a break for half an hour, and we can meet at 11 for Professor Vyach's talk.